The current is flowing basically in this circuit. If you see the current is flowing, current, this is a basically if I assume the current is flowing from this direction, then at this junction it will be splitting. So suppose this is the current I flowing through the circuit. I can say it is splitting over here. So some part of the current will go here, some part of the current will go here, and some part of the current will go here. Because this is a parallel combination, we know in the parallel the currents are split. So I can consider this as I1, I can consider this as I2, and I can consider this as I3. So I is split into I1 plus I2 and I3. Okay. So this way the current is flowing in this circuit. And at this junction you can see this is I1, I2, I3 all will unite, and again they will become I here, and I again flow to the circuit. So we want to find out the current in the fuse. Okay. That's why I have drawn this current. The current is flowing through the fuse is what? It is nothing but the I, and since these are connected in the parallel combination, I is split into I1, I2 and I3. So what is the I basically? I is nothing but I1 plus I2 and I3. Okay, and since the bulbs are identical, they are having the same rating, and we have just found out the current flowing through any of the bulbs, that is nothing but 0.18 ampere. So what is the current that should be flowing through the fuse? So that is nothing but I1 plus I2 plus I3, right? So that's why our current in the fuse will just come out to be, the total value of I will come out to be 3 times, that is nothing but 0.18 plus, you can write down 0.18 plus 0.8, that is nothing but 3 times 0.18, right? So here our 3 times 0.18 is coming out to be 0.55 ampere. So current flowing through the fuse is 0.55 ampere, because it is nothing but the addition of current flowing through each of the lamps, okay, because it is already split. So this one will be the current flowing through the fuse. Now the total number of lamps all in parallel that could be connected without blowing the fuse. Okay, so we know that see here only one fuse is there, and the rating of the fuse is given. This rating is very important in this case. There's nothing but the 2 ampere, and 3 lamps are connected. Okay, and each lamp is drawing the current of 0.18 ampere, and the rating is 2, where the rating of the fuse is 2. So how many lamps can be connected? That means how much load of the current it can bear. Okay. So if there are 3 lamps, we have already found the 3 lamps. The current is nothing but 0.55 ampere is flowing through the circuit, but it can sustain, or it can tolerate the value of current that is equal to 2 ampere. Okay, because its rating is 2 ampere. So we need to find out how many lamps can be connected. If you connect the lamps in parallel combination, okay, the currents will be added, and we can add those many number of lamps. Okay, for that the total current will be equal to 2 ampere. So how many lamps we can add? We can find out this value by just simply dividing 2 ampere current, that is the rating of the fuse, by this current flowing through each lamp. Okay, so I can just find out simply the number of lamps here. Can find out the number of lamps should be equal to 2 divided by 0.18. 2 divided by 0.18. So that will give you the answer of nothing but approximately 11.1. That means the lamps should be equal to 11, because this lamp is the integer. So we can connect, we can't connect 11.1 lamp, we can connect 11 lamps. So our final answer should be 11. Okay. So here I hope you understood this problem. What we have done, if each bulb is drawing the current of 0.18 ampere, and how much load the fuse can sustain or bear, that is nothing but the 2 ampere. So how many lamps can be connected? So we can connect 2 divided by 0.18 lamps, that is nothing but 11 lamps. I hope you understood this problem, and now we will move towards the part B. So this is the part B of the problem. You can read here. After the long period of use, the wire filament of one of the lamps becomes thinner. Underline the effect of this change on the resistance of the filament. So we had seen in electrical quantities that relation of the resistance with the length of the wire and the cross-sectional area of the wire. So this is the wire, the cell is the length, A is the cross-section area. So R is directly proportional to the length and R is the inversely proportional to area. So we are making the wire thinner here. If we are making the wire thinner, that means we are basically decreasing the cross-sectional area. Okay. And if you decrease the cross-sectional area, what will happen? The resistance will increase because this is in the inverse proportionality with the area. Okay. So when it becomes thinner, this area will decrease, and when the area decrease, the resistance will increase. So this one will be our answer, and we have to underline the answer. So resistance increases. Now the second question in the part B, the state and explain the effect of this change on the power of the lamp. So we have already seen the power formula is VI or V square R or I square R. Okay. So in our circuit, what is happening, basically our voltage is constant. So I can use, in this case, I can use this formula V square R. You can take the help of this formula because the our potential remains constant in our circuit. So I can say this P is nothing but equal to P. You can write P is nothing but this formula. You can write down P is nothing but V, nothing but equal to V square by R. So here, what is happening in our circuit, basically we have seen the resistance is increasing. So I can write down as the resistance increases. As the resistance increases, what will happen to the power? Power decreases. Why it is decreases? Because it is nothing but the inverse proportionality. It is, what is the relation between the power and the resistance? P is inversely proportional to R because R is in the denominator. That's why if the R increase, P should decrease. So we have used this formula, that is V square by R, because our V square or V potential difference across the bulb were constant. We had seen the bulbs were connected in the parallel combination and the power supply was fixed, that was 220 volt. That's why the potential difference across bulbs should remain constant, and that's why V square is a constant and P is inversely proportional to R. We can also use this another formula also, P is equal to V into I, and we can also explain, since I decreases in the circuit because resistance is increasing, I should decrease, and that's why V into I is decreasing, that means power decreases. So you can explain in either way. This one is a simpler way, so I explain in this way. So now we will move towards the next problem. Now the question number 3 in the structural problem. The circuit in the figure 7.1 includes an immersion heater and a 6-volt battery. So we can say this is a circuit, this is a 6-volt battery is connected, this one is the immersion heater, this is ammeter connected in the series to measure the current, and this is another component which is connected over here, and this one is nothing but the switch. So if you remember, what is this kind of symbol representing? You can see this question part A, state the name of the purpose of the component X. So if you have only the rectangle, it can be the register, and if you draw an arrow